Hello everyone. In this session, we are going to see another aspect of the network layer or another function of a network layer, that is routing of the packets. Now, routing means choosing the best possible route to deliver a packet towards the destination. Until now, we have seen that IP can be enhanced to support the mobility of the nodes within the network. Now, after choosing the mobile IP, there will be multiple paths available for delivering the packet to the destination. For example, from home agent to mobile node, there can be multiple options available for delivering the packets towards the mobile node. Now, two protocols that we are going to discuss in this particular session, DSDV and DSR. But before discussing them, let's see how this routing is different in mobile networks compared to the wired networks. So routing in wireless or mobile network is different and importantly more complex than wired networks. Now why is it that? First reason is that devices in the network are mobile, plus channel quality always changes. In fixed networks, the link between the two nodes is a physical medium. So it stays same throughout the existence of a network. For example, if you attach a coaxial cable between node N1 and N2, it will provide the same quality throughout its existence. But in mobile networks or wireless network, there is no physical medium, so channel quality may degrade over a period of time. Apart from that, all the nodes within the network, considering this one as our first network, all the nodes in this network may be mobile one. So because of that, topology may change depending on their mobility. Right now you can see it is having a mesh kind of or hybrid topology, where first 5 nodes are in a mesh topology and two further nodes are hierarchically added to the first 5 nodes through node 3. Now that can change over a period of time. So a best route towards node 4 or node 5 or node 7 or node 6 may change over a period of time. That is the first reason. Okay. So the next one, why it is more complex in wireless network. The separation and merging of network is possible in case of mobile networks. In fixed networks, all these nodes will be stationary, N1 to N7. They will not change their position frequently, or very rarely they will change their position. Now, because of mobility of these devices or these nodes will change their location frequently, and that uh, may possibly result into separation of a network or merging of two network. For example, let's consider this first network. Currently it has a 7 nodes at time t1. Now after some period of time, at time t2, two nodes, that is n6 and n7, now n7 which is connected to n3 is now separated from a network, and they form their own network consisting of only two nodes. So at time t2 there are two networks, at time t1 there is only one network. So this is separation of network, and because of that path towards n7 is not possible for first 5 nodes. Okay, so while designing a routing protocol for such network, you have to keep in mind that the network topology may change. Also, the number of nodes in a network may also change over a period of time. So that concludes the second reason. Then third reason is that asymmetric connections are also possible in the mobile network. What do you mean by asymmetric connections? As we have said in the first one, the channel quality keeps on varying. Now in the fixed network, there is a fixed physical medium between the two nodes. Okay, so whatever data rate it is providing in the forward direction, same data rate will be provided in the backward direction. So it is called as symmetric connection. But in wireless network or in mobile network, like you can see in this one, there is a forward connection from N1 to N4, but there is no connection possible from N4 to N1 directly. So that is called as asymmetric connection. Okay, because it is not a physical medium which is connecting N1 and N4. It is a wireless medium, so there is no link present between N4 and N1. So that is the reason mobile network is more complex compared to wired network. So routing protocol must consider only forward link for this particular N4 and not the reverse link. Then fourth reason why it is more complex is that sometimes there may be absence of infrastructure to support routing. What does this mean? That absence of infrastructure. Now, routing protocols in fixed networks are implemented by generally routers. There is a central entity which implements these protocols that decides how a packet will be delivered to a destination. So nodes do not need to worry about how they are going to deliver a packet to the destination. Nodes will simply deliver a packet to router and router will deliver a packet to the destination. But in mobile network, there is a type of network, for example, a ad hoc network, there is no central router present. For example, access point in the Wi-Fi. Whenever we connect to the access point, all the communication happens through the access point, which is nothing but a router. But in mobile ad hoc networks, there is no access point. That means routing should be implemented by each and every node within the network. So, for such situation, routing protocol must be lightweight so that it can be handled by each node present in the network. Okay, so these are primary four reasons why it is different and complex in mobile network to implement routing compared to the wired networks. Then which are the fixed network protocols which we have seen previously in the previous semester. For example, traditional routing protocols which are designed for fixed network, this is important, they are designed only for fixed network because they don't consider all these parameters while delivering a packet to the destination. So which are them? We have seen RIP, that is routing information protocol, which is based on a distance vector algorithm. So primarily it considers distance between two nodes for deciding which is a good path for delivering a packet to the destination. Okay, then OSPF, that is open shortest path algorithm, that is based on link state algorithm, which decides the status of the link, that is channel quality, error rate and all other parameters, and based on that it decides shortest path towards the destination. So these protocols are incapable of delivering the same performance in the mobile network because of these four reasons, at least four reasons which we have mentioned just now. Okay, so we are going to see two new protocols which are somewhat modification of all the fixed network protocols that we have seen previously. So first of them is DSDV. DSDV stands for Destination Sequenced Distance Vector Routing Protocol. So it is abbreviated as DSDV. As you can see from the name, it is based on distance vector routing. That means distance between two nodes will be considered for delivering a packets. So what is it? So DSDV routing protocol is a enhanced version of distributed Bellman-Ford algorithm. Now distributed Bellman-Ford algorithm you might have studied in information security or system security or previous semesters somewhere. Now it is a slightly enhanced version of that particular algorithm. So what is enhanced in that one, that we will see. Now, what happens in the DSDB is that each node maintains a table that contains the shortest distance to every other node. So if there are 5 nodes, then N1 will keep a table that will contain 4 rows for each row for each other node in the table, N2, N3, N4, N5. Okay, so shortest distance to each node in the network is maintained. Apart from that, what is the first node, that is next node, on the shortest path to every other node. So if we have to deliver packet from N1 to N4, what is the next node that will receive the packet in order to deliver the packet to N4? That is also is mentioned in the table. Now what enhancement is done to the Bellman-Ford or this distance vector routing? DSDB adds two major things to the distance vector algorithm. First one is a sequence number. Now sequence number is a phenomena we have seen previously. It helps to apply all the packets in correct order. Here it is mentioned that advertisement, but it can be packets also. Now why this is required? Because if there is a mesh topology, initially it may be star topology, but it may turn out to be mesh later on, as all the nodes are mobile. So over a period of time the topology will change, it may form a mesh. Now for example, if we are considering node 1 to node 4, there are two paths. Okay, so whenever a node 1 is trying to discover a path to node 4, it will obtain two paths towards node 4. So node 4 will find a request twice from the two different paths from node 1. Okay, what usually happens in DSDB is that to find a path towards the destination, each node broadcasts an advertisement for knowing what is the path towards the destination. Okay, so node 4 will receive two advertisement from node 1. Now both advertisement will contain same sequence number, for example 47. Now when node 4 receives two same advertisement having same sequence number, it will realize that there is a multiple paths available, so it will discard one of them. Okay, so it helps to apply the advertisement in correct order. Sometimes what happens, second advertisement is also sent and it appears later to the first one, or sometimes second advertisement comes first and first advertisement comes second, depending on distance between the two nodes on the first path and the second path. Let's say there are multiple nodes in the first path, so it required larger time to reach the node 4 compared to second path. So second advertisement came in first and first advertisement came in second. So in order to apply a correct decision, a node 4 should know which is the first advertisement which should be replied first and which is the last advertisement which should be replied last. So sequence number helps in deciding that thing. The second factor that is added by DSDB is a damping. Now what is damping? Now sometimes it may happen that node temporarily moves or changes its location within the network. For example, this is a node that changes the location, it moves here for a very short period of time and then come back to its original location again. Now in that case, changing the tables for all other nodes is not a good solution. We have seen DSDB asks each node to keep a routing table for each particular destination within the network. So temporary movement of a particular node should not disturb or should not initiate routing table updates for each node. Okay, so that is called as damping. The transient changes in topology, transient means momentary changes in topology that are of short duration should not destabilize the routing mechanism. Just because for a short moment of time a node changed its location entire network should not change their routing mechanism. A node waits with the dissemination if these changes are probably unstable. So, how to overcome these temporary changes? In DSDV, nodes wait a certain amount of time before updating their routing table so that they will get to know whether these changes are stable or temporary, or these are uh, permanent changes or changes for longer time. So this waiting time obviously depends on the time between the first and the best announcement of a path to a certain destination. So that is also another thing. In every advertisement it is mentioned whether what is the distance toward that particular node. For example, first advertisement mentioned distance toward destination is 3 hops, and second advertisement mentions distance is 4 hops, and third advertisement mentions distance toward destination is only 2 hops. So the announcement of best path is in the third advertisement obviously. So a node has to wait certain amount of time before deciding which is the best available path. So that is called as a damping. That is a time in seconds in which during which node will wait for realizing the best announcement of a path. Okay, so these two things are added. Now let's see the working of this DSDV. On your screen you see a network consisting of 15 nodes. Okay, now it is shown a routing table for node 1. Such tables for each node will be maintained by the each node. So there will be 15 routing tables, one for each node, maintained by the nodes within the network. So the routing table for node 1, which is this one, is shown over here. Now there are 15 nodes, so remaining are 14. So you will see there are 14 entries in the routing table. First column is destination. Destination means if node 1 has to send a packet to node 2, what should be the criteria? If it has to send a packet to node 8, what should be the criteria, and so on. Okay, so what we are seeing in this particular table is that second column is the next node. As we have seen, the next node, if I have to send a packet to node 11, let's say where is node 11, this is node 11, there are multiple paths available like this one, then this one, then this one, this one. There are so many paths. Now out of this, one of the path must be mentioned, and the best path is right now mentioned as best path right now is mentioned as destination is node 11 as it is seen. The next node is 6, that means along this path the best path is available. Distance is 3, the next column is distance. Now how it is calculated? This is first hop, this is second hop, and this is third hop. This distance is the smallest distance available, so 3 hop is a distance, that is for node 11. Then finally the sequence number. This is not an entire routing table, only the major elements of this routing table are shown in this diagram. The sequence number is a random number. This is the number indicating the advertisement ID. Okay, so it will change over a period of time. So these are the basic 4 entries which has to be present in the routing table. Okay, so like this you will see for node 2, next node is 2 because this is the shortest available path. Distance is 1 hop, sequence number is 22. For node 11 we have already seen this is the best path. Similarly you can find for node 15, that is for this node. Next node is 5, that means through this path you can travel. The distance is 4, that means within 4 hops you should deliver to the destination. So most probably the path should be like this. This is the shortest distance. This is also giving you the 4 hop distance, but the distance between node 12 and node 4 is larger than distance between node 10 and node 12. So I think this will be the best path towards the 15th. Okay, so this is how each and every one will maintain a routing table. Now what happens when a node changes the topology or some of the nodes move from their original location? For example, we will take node 11 which moves from the original location. Let's say the broken link case. So if one of the link between two nodes or more than two nodes is broken, what happens? Each node upon receiving an routing table update quickly disseminates it. So if node is detached from another node, it will broadcast a routing table update to nearby neighbors. So these neighbors will receive the update, update their own routing table and further broadcast the update to their neighbors in order to propagate the broken link information to the whole network. So whatever changes that are happened, they are broadcasted step by step into the entire network. Thus a single link break leads to the propagation of table update information to the whole network. So even if a single link is changed, the entire network will update their routing table. We can say this is a kind of a drawback. Why? We will see that. So all in all, this we can say that DSDV is a table driven routing protocol, because every node has to maintain a table and deliver packets according to the entries in the table. Okay, so how this uh, protocol will work after link is changed or link is broken? Let's see that example. So this is the same network that we have seen previously. Now routing table for node 1, we have seen node 11 had a best path 1 6 10 11, which had a distance of 3. Next node 6, destination 11. Forget about sequence number. Okay, so these are the three entries that we have seen. Now let's see what happens. Now node 11 has moved from its original location. Again I am showing node 11 is moving out of its original location to some other location. So it has moved from here to here. Now once it moves here, it will again broadcast a table routing update to inform that it is now detached from the node number 10 and 14. So it will broadcast. So as you can see circle, it is broadcasting. Now 10 is too far away from node 11, so it will not receive this broadcast. 14 will receive this broadcast. So what will happen? So it will receive or form a link between 11 and 14, and further that 14 will broadcast the information to its neighbors like 15, 12, 10. They will further broadcast the information to their neighbors and so on. So that is what it is shown. Now does that change a routing table? Previously it was 11 6 3. Now let's see what is the routing table update. As you can see, now 11 has a next node 5 and distance is 4. Okay, so this is the shortest path available for the routing the packet towards the node 11. So this is how it will work. Every time or every node will implement this kind of update. This update is shown for only node 1, but for node 2, node 3 and so on, for every node there will be a routing table update. So this is how DSDV works. Okay, I hope it is clear. Let's see what are the advantages and disadvantages of this one. Now the updates are propagated throughout the network in order to maintain an up-to-date view of the network topology at all the nodes. Hence, we observe less delay in the route setup process. So in order to deliver a packet to a destination, first path that is adopted by transport layer in case of TCP if we are using is setting up a connection. So if path is already known, then connection can be set up immediately. So this is very advantageous for transport layers to have a DSDV at the network layer, because paths will be already known to the transport layer. So that is the advantage. The second thing is that if even though we are maintaining the tables at every node, it is slightly complex. So let's say disadvantage: DSDB suffers from excessive control overhead. Excessive control overhead means for single link breakage, entire network has to update their routing table. So amount of control packets that are exchanged within the network are too many. So that is proportional to number of nodes in the network. So if there are 15 nodes in the network, as we have seen in the last example, a single broken link will be broadcasted several times in proportion to these 15 nodes. Okay, because every node has to update their routing table. So that generates too many control packet in the network. Okay, so therefore it is not scalable in ad hoc networks. What is ad hoc network we will see later on in the fourth chapter. But these ad hoc networks have a limited bandwidth because there is no central router, so each node has a limited capability, so limited bandwidth is available, and their topologies changes frequently, or their topologies are highly dynamic. That means if there are 15 nodes and they are frequently changing their location, for example, if you are forming the network uh, in a stadium, or rather than stadium, in a fair where people are moving here and there several times, then it is a highly dynamic network where changing the routing table information so many times is not a feasible solution. The next disadvantage will be, in order to obtain information about a particular destination, a node has to wait for table update message initiated by same destination node. So whichever node detaches from another node has to initiate a table update message, and it has to propagate through entire network in order to update the routing tables of all the nodes. So this could be very long process, and it will generate a delay that can result into a stale routing information at nodes. Now what is stale routing information? That means, as we have seen, the node 11 broadcasted the table routing update. Now by the time it reaches node 1, suppose 5 seconds are taken, and before it reaches node 1, node 11 again changes the position within these 5 seconds, so it will again broadcast the update. So once node 1 receives the update, it becomes irrelevant because node 11 has further changed its location to some new location. So it is whatever update that received by the node 1 is now stale, that is old one, because node 11 is no longer at the same position. Okay, so it may generate a stale routing information also. So how can we overcome these drawbacks, and how can we keep these advantages as it is? That is the next point of research, and that's why we will see now the next protocol, that is dynamic source routing. In mobile IP encapsulation, we have seen a GRE encapsulation technique where there was a bit named as small s, which in which in which told us that strict source routing is used. Now what is source routing? In GRE header there was a field named as small s, one bit field, which told us that strict source routing is used. Now source routing means route towards destination is strictly decided by the source, not anyone else. Okay, intermediate nodes will follow only whatever is told by the source of a packet. Intermediate nodes cannot decide alternate paths for delivering a packet to the destination. So that is strict source routing. So based on this source routing, there is a dynamic or DSR, dynamic source routing protocol, which splits the routing into two steps. First is a discovering of a path, and then maintaining the discovered path. So in the first step, whenever we have a data to transmit, only then we will find out a path towards the destination. Unlike DSDV, DSR does not maintain a routing table for entire period of time. Okay, in DSDV, the routing tables of each node are updated regularly. Such routing tables are not maintained in the DSR. In DSR, whenever a node has a packet to deliver to a particular destination, it will start finding a path towards the destination. So that is nothing but discovery of a path. So don't waste network bandwidth for exchanging control packets. That is kind of a advantage of this particular DSR. Okay, so only if a path for sending packets to a certain destination is needed, that means whenever you have a packet to be delivered, then only path is discovered. Otherwise, don't discover path. And if no path is currently available, that is also important. First time you will discover a path, later on sometimes you will stop sending the packets for certain period of time, and after some time you will again want to send a packet. At that time you already have a path, so don't search for a path all over again, because you already have a path. That is the assumption made by the DSR. Okay, so that is how discovery is done. Then maintaining a path. Once path is discovered, it is job of the source to maintain that path. So when the path is in use, everyone within the path has to make sure that it can be used continuously. So along the path, if intermediate nodes move away, so suppose this is source, this is destination, if this node moves away, then it has to inform its neighbors that it is going away from the dedicated path. So source will know again, and that will find a new path. Okay, so that is the maintaining a path. So what is the advantage of this one? Advantage of this DSR mechanism is that we don't need to send periodic table routing updates, because there is no routing table maintained by the nodes. So less amount of control overhead, that is one of the advantage. Hence we can call DSR is on demand, because whenever we need a path, then only we are finding a path. That is on demand distance vector routing protocol. This is also part of a distance vector routing. So number of hops will be important in this one, but the path is discovered only when it is needed, that is on demand. So this is on demand distance vector routing protocol. So let's see how this works. First, path discovery. How path is discovered? First of all, whenever you have a packet to send, broadcast a packet with the destination address and unique ID. So I am a node 1. I have to send a packet to node 7. I will broadcast a sample control packet which will mention N7 and its unique ID for this particular control packet. Let's see 123. Okay, now all the nodes within the network which are connected to N1 will receive this particular broadcast packet. If the station receives a broadcast packet, if any station within the network receives this broadcast packet, two things it will check. First thing, it will check the destination node. If a station is the receiver, if N7 receives it, it will know that this packet is for me. That means someone is trying to send a packet to me, that is has a correct destination address. Then return the packet to the sender. So whoever sent this packet to me, I will return this packet to the same sender. Okay, second condition, the intermediate nodes. If the packet has already been received earlier, which will be identified via ID, sometimes because of looping you will receive multiple packets of same unique ID. In that such case, discard the packets which are received later on. So to avoid duplication, we will discard all the packets which are received later on or further on after receiving the first packets. Then third thing that is done after receiving a packet, if intermediate node like let's say N4 receives a packet, it will know that it has to be delivered to N7. I am not N7, but I can connect to N7. Then it will append its own address and broadcast the packet. So it will forward the packet to N7. Okay, ID is kept same. ID will not be changed because it is a unique one and it has to be maintained throughout the path. So like this, intermediate nodes will keep forwarding the packet and finally destination will receive the packet and return it on the same path. So whenever such packets are forward, each intermediate node will append its own address. So if the path is N1, N2, N4, N7, by the time N7 reaches or receives the packet, it will have a path which will be mentioned as N2 or N1, N2, N4, N7. This path will be collected at the destination. Okay, so that is how discovery of a path is done. Sender receives the packet with the current path address list. When N7 returns that packet on the same path as mentioned during the collection or reaching towards the destination, this address is received by the N7. The same address or same path is returned and sender will receive and get to know what path it had traveled to the reaching towards the destination. So sender receives a packet with current path or address list. So it will receive N1, N2, N4 and N7. We will see one example. Sometimes there are certain optimizations are done in order to conserve the bandwidth. For example, limiting broadcast if maximum diameter of network is known. If a network is small one, number of broadcast packets are reduced. Sometimes caching is also done for keeping the path information. Then that means nodes keep a cache where already known paths are stored. They are regularly updated. The cache is flushed out and new paths are updated in the cache in order to save the time. Then third optimization can be station can use the cached information for path discovery, own paths or paths for other hosts. That's what I said. This cached information can be used for saving time to deliver packets to other hosts or to receive the packets from the source. So this is path discovery. Let's see how it happens. Consider this example. So these three are irrelevant, which are not part of our network. Now sending from C to O. This is my source and this is my destination. So first step is route discovery. Now route discovery, that means first C will broadcast a packet to its neighbor containing destination address and unique ID. So let's see what happens. So broadcasted a packet to neighbors. Now first entity is destination, that is O. Second is where it is come from, that is C, and the unique ID is 4711. In the case of node B, destination is node O, where the packet has come from, that is C, and then unique ID. Similar will happen in case of E. The information will be OE4711. Okay, now next, all these nodes will broadcast the packet further on. So G will broadcast to I, G will broadcast to E. Similarly, E will broadcast to G, E will broadcast to C also, and E will broadcast to H. At the same time, it will broadcast to D also. B will broadcast to A and D. Like this, it will keep on broadcasting. So now at I, what is the information that is received? Now path is traveled is this one. So information received is destination is O, path traveled is CG, and unique ID is 4711 as it is. Similarly, it will go on like this. At each node, broadcasting will happen, path will be updated like this, and finally it reaches node N and node O. Now node N realizes that it cannot reach node O, so it will discard the packet. Node O realizes that I am the destination because first field is O, so it will collect the packet and collect the path traveled by the packet and return the packet. Okay, so this is the best possible path that is obtained. So path is MKIG. MKIG, that is the path on which packet is returned, which is received by C. Packet path is updated and actual data can be now forwarded on this path. Actual data is forwarded on this path in order to deliver that data to node O. Okay, so this is how route discovery is maintained. Now, how to maintain the path? That means how to understand whether path is still existence or any node has moved on. After sending a packet, each node will wait for layer 2 acknowledgement if it is applicable. That is, you will wait for acknowledgement from data link layer whether packet is received by anyone or not. If acknowledgement is received, that means path is still existence. Keep listening to the medium because data link layer will also implement medium access mechanism, so you can keep listening to the medium to detect if other stations are forwarding the packet or not. So this is also depending on what is the medium access mechanism that is implemented on data link layer or layer 2. Then if you don't hear any acknowledgement of certain amount of time, we can request an explicit acknowledgement from the neighboring nodes. So if they have not received an acknowledgement, they have not received a packet, they can send a negative acknowledgement. If they have received a packet, they can send acknowledgement. Okay, then this is how we can know whether the nodes are still connected or not. If any node is moved out, it can inform the sender so that sender can look up for a new path locally. Okay, so this is how paths will be maintained. So first part is discovering a route, and after discovering, while sending the actual data, maintain the path by using these mechanisms. So this is slightly complex compared to DSDV, but amount of control overhead which is generated within this protocol is very less. So it is highly scalable as well as it can work very well, or it gives a very good performance in case of highly dynamic mobile networks. Okay, so this is about network layer. We have seen what are the enhancement needed to be done to IP and how different routing protocols are needed for delivering packets into the network, that is particularly mobile network. Okay, so that's all about network layer. In the next session we will start with the transport layer. That's all for today. Thank you.